Hello friends, so today we are going to once again solve the questions, 3 questions rather, and all these 3 questions are from rotational motion. Okay. And one second. So in this question, let me check whether everything is working or not. Okay, so it looks good. So the first question, we are given that a mass is attached to a massless string moves in a horizontal circular path as shown in the figure. The length of the string denoted by L is slowly varied, either increased or decreased, so that the system remains in quasi-static equilibrium. The quantities theta, L, R and H are defined in the figure, and it is also mentioned that theta is the angle the string makes with the vertical, R is the radius of the horizontal circular motion, and H is the vertical height of the mass above the reference level. So based on this, we are having 2 questions. Part A, when theta is very small, how does the radius depend upon the string length, that is L? And when theta is close to pi by 2, how does the height H depend upon the string length? So this is the basic question, and we can say draw the basic diagram also. The diagram is quite simple. So this is our support and the vertical, and we are having a string which is rotating in a circular path. Okay. So something like a conical pendulum, and suppose this is the radius R of this conical pendulum, and H is the height, theta is the angle with the vertical, and L is the length. So these are the things given to us, and we are having this is a small bob of mass M. Okay. Anything else? Yeah. So string is massless. Okay. So in this case, we are supposed to find out the 2 things. When theta is very small, what is the relationship between the radius and the length L? And when theta is close to pi by 2, what is the relationship between the height H and length L? So first of all, from the figure itself, we can write that our this radius R can be written as our L sine of theta, okay, and H, that is height from the base, can be written as L cos of theta. And we are going to use these 2 particular relation at the end of the solution. And it is said that the length is either decreased or increased very slowly, so the system is always in quasi-static equilibrium. Okay. And when it states that theta is very small, so it basically means that this value of theta is approximately equal to 0. Okay, it means the string is entirely vertical. Okay. And when it says theta is close to pi by 2, so it means the string is entirely or approximately horizontal. So these are the basic 2 conclusions which we can draw. And first of all, we are going to find out the relationship between various forces acting on it. So for that, we have a tension T on the string, and with the vertical it is making an angle of theta. So the other angle, this angle will be also theta. So we can divide this T into two components, will be T cos of theta, and the second component will be T sine of theta. And we are going to have our mg that will be acting in downward direction. Okay. So therefore, we can write that our this T cos of theta is equal to mg, that is a vertical component balance. So we can say our vertical component balance, and this gives us that our T cos of theta is equal to our mg, and the horizontal component is going to provide the necessary centripetal acceleration. Therefore, we can write that our horizontal component provides centripetal acceleration and from here we can write that our T sine of theta will be equal to m omega square times r. And from, if we divide these two equations, let us call this equation number 1 and equation number 2. So we can write from equation 1 and 2, from equation 1 and 2, we can write that our this tangent of theta will be equal to, we get this as m omega square r divided by mg, and we can cancel out our mass here, and we can further write it as our tangent of theta is equal to, we can write our angular in terms of tangential velocity v. Therefore, let us reformulate it as our, this will be our v square r square multiplied by r, and here this r cancel with r square, and we are left with term g. So this we can multiply on the other side. Therefore, from here we get that our v square is equal to rg tangent of theta, and from here we can easily calculate our angular velocity. Therefore, we can write that our omega square will be equal to g tangent of theta divided by r, and we can find out the angular momentum about the vertical axis. So we can say that our angular momentum about vertical axis and this angular momentum, let us say, is of L. So L will be equal to over m r square multiplied by omega, and we can substitute value of our omega. So this comes as our m r square, and it will be g tangent of theta divided by r and its square root. And from here we can write in terms of our, this comes as mr, and this will be 1 plus 2 plus rather, it will be our 2 minus 1 by 2. Yeah, so 2 minus 1 by 2 is going to give us 3 by 2 and square root of g tangent of theta. And so if we square both sides, we are going to get our L square will be equal to our m square, and we have our r cube, and this comes as g tan of theta, and tangent of theta is nothing but our r upon h. So we substitute it, we get this as our m square r cube times g multiplied by r upon h. So from here we get this as our m square r times 4 g upon h. Okay. And we can rearrange it, and this rearrangement gives us that r raised to power 4, and one second, let me write it once again here. So we get this as our L square is equal to, we have this as our m square r raised to power 4 times g upon h. Okay, so therefore we can write that our r 4 upon h will be equal to L square upon m square times g, and this, all the terms on our right side, this entire terms are constant, therefore we can write that our r raised to power 4 times h is equal to constant. And yes, so now we come to our first part, part A, and in part A our theta is approximately tending to 0. It means the string is almost vertical. If string is also almost vertical, so we have already written the relationship that our h is equal to L cos of theta. So from here, if theta is approximately equal to 0, therefore we can write our h is approximately equal to our L. And therefore we can write, let us call this equation number 3. So we can say from equation 3 we can replace h by L. We get this as r raised to power 4 divided by L is equal to constant. And from here we get that our r is proportional to L raised to power 1/4. So this is the relationship between our this radius as well as our length. And we come to the part B, and in part B it said that theta is approximately equal to pi by 2, and for that we can use the relationship that our r is equal to L sine of theta. So if theta is close to pi by 2, therefore we can say that our r is approximately equal to L. So once again, from equation 3, so we can write from equation 3, we can replace our r by L. So this comes as L raised to power 4 divided by H is equal to constant. Or from here we can say that our H is proportional to L raised to power 4. So this is the relationship between the radius and length as well as the height as well as length. That was asked in the question. So this was the first question. We come to the second question, and in the second question it states that we are having a, you can say, chimney is given to us that is a tall chimney initially stands upright. After receiving a small kick, it begins to topple. To analyze this, consider the following simplified two-dimensional model. The chimney is represented as a vertical stack of rigid boards, one on the top of another. Each board is connected to its neighboring board by a small rod located at its two ends, as shown in the figure. You may assume the width of the chimney is very small as compared to its height, so that the motion essentially is a planar motion. So the question is, at what point along its length is it most likely to break? So this is the basic question, and here it is given that we can consider that the chimney width of the chimney is very small as compared to its height. So ideally we can consider that chimney is nothing but a single rod. Okay, but we start with the basic figure that is given to us in the format of chimney. Okay. So we can just draw the basic figure, and it says that each, you can say, there are a vertical stack of rigid boards. So we can draw the vertical stack of rigid boards. So these are the vertical stack of the rigid boards, and these vertical stack of rigid boards are connected by individual rods. Okay, something like this. So this is the, you can say, magnified version of the figure, but in this case it is given, and for the sake of convenience let us assume that H is the height and the width is 2r. Okay. And this width is very much smaller as compared to the height that is given in the question, and for that we can easily consider that it is nothing but a single rod, which is something like this, a vertical. And when it is given a slight push or kick, as it is mentioned in the question, so let us assume that it is at this particular angle and making angle of theta with the vertical. And so we can consider this building as a thin rod. Okay. So we can consider that our chimney is nothing but our thin rod. This approximation we are going to make. So let's find out what will be its angular acceleration. And therefore we start with the angular acceleration. And angular acceleration, we can say nothing will be a double derivative of this theta, that is angle of inclination, and it is going to pivot about its end. Okay, let us call this as pivot point P. So we can write that the moment of inertia of this chimney about the pivot point P. So the moment of inertia of chimney about point P, and let us suppose that is our I, which will be nothing but our 1/3, and let us call this not H, but let us redefine this as L, length L, and this comes as 1/3 ml square. Okay. And obviously we are going to have the center of mass is suppose somewhere here, so mg will be acting in the downward direction, and the length of this mg from the pivot point is of L/2, so it is going to produce a torque. Therefore we can write that the torque due to gravity, let us call this as our tau, and tau will be equal to our mg, and the length of the lever arm, the perpendicular lever arm, that will be over L/2 sine of theta. And from here we can write the equation of the motion. So we can say that our equation of motion, and we can say that our moment of inertia will the torque is equal to, so we can say that our torque is equal to moment of inertia, and we have a double derivative of our theta. And torque we already know, moment of inertia we also know, so we substitute both these values or equations. So torque is our mg L/2, and this comes as our sine of theta. Moment of inertia is our 1/3 ml square, and multiply by double derivative of its angle. Okay. And from here our this mass cancels with mass, length goes by the square, therefore we get that our double derivative of theta will be equal to, this comes as our 3/2 g sine of theta. Okay. So we are going to use this particular relationship later on. Now it says that the chimney is going to break, so let us assume that, so we have the initial position of chimney that is vertical, and the chimney we assume that it breaks at somewhere here, and we say that its bottom part is having a height h, and total length we know is our L. Therefore the upper portion will be equal to our L minus h. Okay. And so as soon as, so therefore we can write for the upper portion that the upper portion is, suppose is, this is the center of mass of the upper portion. So this center of mass is going to rotate in some kind of circular path, and its distance, this distance will be our L minus h upon 2, and we can easily find out the distance of this circular path from the point of pivot. Okay. So let me write it here, and then we can easily calculate. So we consider that chimney is having two parts. chimney is having two parts, and we consider the bottom part, and this point we know is our P. So this common point, let us call this as Q, and this furthermore part is our R. So bottom part is our PQ, and we consider that the height, the length of this bottom part is our H, or we can say the height is our H. Therefore, we can write that our top part, that is our QR, will be also obviously equal to total length of the chimney, that is L minus H. And for the sake of convenience, let us assume that the ratio of this H upon L is given by a factor F. Okay, so this we have assumed, and we are going to use this F factor in all the calculation for the further. Therefore, from here we can say that the mass of the top part, mass of the top part, and top part is of QR, will be equal to, this will be 1 minus F multiplied by total mass M. And we can also say that the center of mass of top part, and top part is our QR, and the center of mass of this QR is, let us suppose, our O. So we can say center of mass, that is our point O of the top part, travels in a circle of radius, and we can easily find out its radius. Okay. And like we said that our this QO will be equal to LH upon 2. So we can say that our QO will be equal to L minus H divided by 2. Therefore, we can write that our PO will be equal to H plus L minus H upon 2, and this gives us L plus H upon 2, and the radius of the circle radius, and this radius is our PO, and we are going to find out the value of PO. And this PO we can just rewrite it as that our PO, we can take L as common, so this will be L by 2, and this comes as 1 plus H upon L, and our H upon L is nothing but our F. So we can write this will be equal to L upon 2 1 plus F. So this is the radius of the center of mass of the top part. Okay, so this we found out is equal to 1 plus F L upon 2. Okay, that is our PO. And let us draw the various forces that will be acting on this chimney. Okay, and for that we are going to draw the broader version of this chimney, and so chimney is in two parts. It will be something like this, and this is our second part. Okay. And so therefore, other than the mass, there will be two forces, or rather we can say three forces acting on it. There will be tension 2, which will be nothing but the longitudinal component along the chimney, that is tension T1 and T2, and other one will be the transverse component that will be perpendicular to the chimney. Okay, so these are the three forces that will be acting on it. So therefore we can say, or we can say that this is our T1 and we have a T2, and the force will be the perpendicular component. Okay. So let me redraw this in the form of a single rod. Okay. And we are mainly interested in the upper portion, so we are going to draw only the upper part. Okay. So we are having this upper part, so this is our Q and this is our R, and the center of mass of the upper part is our O. Okay. And there will be two forces, tension forces. So we are having this as T1 and we are having our T2, and there will be a force F that will be perpendicular to it, and the angle at which this top part will be making with the vertical is our theta. Okay, 1 second. Yeah, it is theta. So this is a angle theta. Okay. And we are having our force mg that will be acting through the center of mass in the downward direction. So this angle will be also equal to theta. So we can divide this mg into two components. One will be our mg cos of theta. Sorry, the mass won't be mg. The mass is our, because total mass is m, and 1 second. Yeah, so mass of the top portion is 1 minus f times m. So it will be coming as 1 minus f times m, because m is the total mass. So this comes as 1 minus f mg cos of theta, and we are going to have a perpendicular component that will be 1 minus f mg sine of theta. Now we can write the equations. So we start with our radial force balance equation. So the radial force balance equation, and we are having three basically radial forces. We have T1, we have T2, and we have component of our mass. Okay. Therefore we can write this as our T2 minus T1 plus 1 minus f, and we have this as mg cos of theta, and that will be nothing but our mass component 1 minus f multi times m, and then we have our we just calculated it as our length is our 1 plus f upon L by 2. So this comes as our 1 plus f upon 2 times L, and we have this our theta derivative square. So this is our radial balance equation, and similarly we can write our tangential force equation. So you can say we are having tangential force balance equation, and for that we can write our f plus, and other force is our the mg component, that is our 1 minus f mg sine of theta will be equal to, we have a 1 minus f times m, and we have our 1 plus f upon 2 times L, and we have the double derivative component. Okay, so these are our two components, and finally we come to our torque equation. Okay. Torque, therefore we can write that our torque balance about center of mass of the top part and top part is nothing but our QR. And so we are having two forces, tension forces rather, T1 and T2, and we assume that this total distance is about 2r. Therefore from the midpoint the distance will be our r, r and r. So there are two forces and the perpendicular distance with respect to the axis is r. Therefore we can write this will be T1 plus T2. Ideally it will be T1r plus T2r. So we can just combine them, T1 plus T2 times r, and we have minus, and this is our force F, and we can write this as 1 minus F by 2 times L, which will be equal to 1 minus F times M, and we can write this as 1 minus F whole square divided by our 12, and this is our L square times theta double derivative. So this is our torque balance equation. And now we come to our approximation that our R is very much less than our L. So we are given a question that value of this R is very much less than our L. So it means that our T1 plus T2 will be larger as compared to our F, and because of this we can say that our T1 is approximately equal to our T2, and therefore we can write the torque equation, and this torque equation gives us about twice T2 times R minus F, and we have 1 minus F upon 2 times L is equal to 1 minus F times M and 1 minus F whole square upon 12. This comes as L square and theta double derivative. Okay. And we are simply going to replace our theta double derivative because we already know its equation. 1 second. Yeah, so this is our theta double derivative, so that is our 3g. Okay, so let me write it here so you can see, but this theta double derivative is equal to 3 by 2 g sine of theta. Therefore we can write the equation that our F will be equal to, we can just solve it, and this is our T2 and okay. So but we know that our this theta double derivative is 3 by 2 g sine of theta, and we are going to solve it for our force as well as our T2. Okay, so force we can write will be equal to our mg sine of theta divided by 4, and this comes as -1 plus 4f minus 3f square, and our T2, we are going to get this as our mgl sine of theta, and this will be 8r and f times 1 minus f whole square. So these are the two equations for our force as well as the tension T2. And in the question we are supposed to find out that what point along length it's the most likely to break. Okay, so it means we have to find out the maximum value of our T2. That's why we found out the equation of our T2. Okay. Because when T2 will be maximum, this particular building has the tendency to break. Okay. And so we can say the maximum tension T2. So we are going to differentiate our T2 with respect to our F. Therefore, and substitute it is equal to 0. So we can say that our derivative of our T2 with respect to our F should be equal to 0. And from here we can say that our F will be equal to 1 by 3. So this is our value of F, and we know that our F is nothing but our H upon L. So H upon L is equal to 1 by 3, or we can say that our H should be equal to L by 3. So it means the building is having the tendency to break from at a distance L by 3 from the bottom. Okay. So that was our final requirement. And okay, that's all. And in this case, if we want to find out value of force F, and we substitute in this equation, if we substitute value of F is equal to 1 by 3, this particular value of F will be equal to 0. So it means when our tension T2 is maximum, the transverse force is equal to 0. So we can just draw a conclusion from there also. Okay. So we can say that our at F is equal to 1 by 3, the transverse force, that is our F, is equal to 0. So it means when our basically when T2 is maximum, this transverse force vanishes. That comes equal to 0. So this was the second question, and we come to our third question. And this third question states that a ball of mass m collides elastically with a stick whose moment of inertia about its center of mass is given as I alpha ml square. The ball initially moves with a velocity v0 in a direction perpendicular to the stick. It strikes the stick at a point located at a distance d from the stick center as shown in the figure. Determine the resulting translation speed of the stick, its rotational speed about its center, and the final speed of the ball after the collision. This is the basic question. This question is comparatively easy. Only difference is that the ball is striking at a distance d with respect to the center of mass. So this is the minor twist in this question, otherwise it is comparatively easy. So we can just draw this. Suppose this is our stick, okay, and we are given that it is having a mass of small m, and its length is our given to us over L. And suppose this is the center of mass of the stick and the ball strike the rod at a distance d from the center of mass. And suppose the ball is moving in this direction and it is going to strike at this particular point. So this is a ball of mass m moving with the velocity of our v0 perpendicular to the rod. So this is the basic question. And we are going to find out other relative parameters based on this question. And so let us write the things which are given to us. So we are given that our initial velocity of the ball is given to us as a v0, and after the collision, let us suppose the speed of the ball is our v. So we can say after collision, speed of ball is suppose v, and the center of mass speed after collision is suppose small v. So we can say that after collision, speed of center of mass is suppose small v, and obviously it is going to have a tendency to rotate about its center of mass, that will be a pivot point, so that its angular speed is our the stick's angular speed is our omega. So you can say that our after collision, angular velocity of stick is, let us suppose, omega. And rest of things are quite obvious from the figure. So in this, basically this question is based on the conservation. The collision is also elastic, so the one additional conservation we can use is our energy conservation along with our momentum, linear momentum and angular momentum conservation. So we are going to start with our conservation equation. So first is our linear momentum conservation, or simpler terms we can say our momentum conservation. And for the momentum conservation, we have a, because initially only ball is moving, so this is initial momentum, and final momentum is of the ball and the center of mass of our rod. Okay. And then we come to the angular momentum. And angular momentum about the center of mass. So we get this angular momentum v0 multiplied by the perpendicular distance d, and then we have its mvd plus moment of inertia is given as alpha ml square times omega. And finally we can write our energy conservation. And this energy conservation is elastic, therefore we can write this as half m v0 square is equal to over half m v square plus center of mass and plus it's our angular part, that is a half alpha half I omega square, and I is our alpha ml square times omega square. So these are the three equations, and everything is going to revolve around these three equations: first equation, second, as well as a third equation. And first of all, we are going to find out the relationship between our this linear velocity of center of mass as well as its angular velocity. So you can say a relation between v and omega, and we are going to start with equation 1. So we can say our from equation 1 we can write that our this small mv, we can combine these mass terms, so we get this as our mv is equal to capital M v naught minus v, and therefore we can write this as a v naught minus v is equal to our m upon capital M times v. Now we are going to use equation 2. So we can say from equation 2 we can once again combine these two parts, and this gives us that our md we can take as common, so we get this as our m times d v naught minus v is equal to our alpha ml square times omega, and we can substitute value of v naught minus v, and we get this as our md times m upon capital M v is equal to alpha ml square times omega, and this capital M cancel out from here, small m goes with small m, therefore we get that our v times d is equal to our alpha L square times omega. Okay. And from here we can write that our omega is equal to, we get this as v upon d, sorry, v multiplied by d and alpha L square. So this is our relationship between our v as well as our omega. Now we are going to solve for our capital velocity v as well as small velocity v, okay, meaning after collision velocity of center of mass as well as that for the ball. So we can say that, okay, so we are going to use now equation 3 and substitute value of omega. So we can say from equation 3, and we have this as our half m v naught, and we have omega square here, so we can substitute this as half m v naught square is equal to half m v square plus half m small v square, and that will be plus half alpha ml square, and this comes as vd upon alpha L square times whole square, and this will be, now we can rewrite it, and we can say that our half m v naught square will be equal to half m v square plus half m small v square plus, and alpha square and alpha are going to cancel out. L square and L4 will be also going away, so we will left with this half, and this will be equal to over d square times m. So this comes as md square, and we are left with this alpha and our L square times v square. Okay, so this is the basic equation. Now once again we are going to use our equation number 1. So once again we can say that from equation 1 we can write that our V is equal to V naught minus m upon capital M times V. Okay. And we are going to substitute this value of V in our energy equation. Okay, and we can just cancel out this half throughout. That is not required. So we get this as our m V naught square is equal to, we have a m and our V naught minus m upon capital M V whole square, plus we have this as our m, and okay, we can combine these two terms and we get this as our mv square, and this will be equal to over 1 plus, and this will be now d square upon alpha L square. Okay, now it's only calculated part. Okay, so I'm going to directly put or write the value of V, because it is going to take lots of space to calculate everything. So basically we are going to get that V, that the center of mass velocity will be equal to twice V naught 1 plus m upon capital M plus d square upon alpha L square. Okay, so this is the our velocity of our center of mass after collision. And we are also supposed to find out our angular velocity, which we already did. So our omega we found out is equal to v times d, and this is alpha L square. And we also find out our velocity after collision, that is our v is equal to v naught minus m upon capital M times v. And if required, it is nothing but calculation. We can substitute value of v in both these equations and solve it further, but that is not required, okay, because that is only going to give us too much of calculations, nothing else. Okay, so I'm directly going to put these two equations in terms of our v naught and substitute value of v. So we are going to get that omega will be equal to twice v naught times d, and this comes as our alpha L square 1 plus m upon capital M plus d square and alpha L square. And similarly we can write our capital V will be equal to, this will be coming as v naught 1 minus, this will be about twice m upon capital M 1 plus m upon capital M plus d square and alpha L square. So these are the velocities of our, this is the velocity of our center of mass after collision, the angular velocity, and the velocity of the ball after the collision, which was asked in the question. So these were the 3 questions for today. Thank you.